Well, welcome to statistics today. So we've got an hour to talk about 3.2. There was one question. A couple of you alerted me to this. There was one question in your 3.1 assignment that asked you to find the standard deviation. And therefore, you were not prepared for that question, but you will be after, well, right now in 3.1. And so you still have time to complete that. And so that hopefully will still be okay. But this is a huge idea. This is an idea that is really the entire course of statistics. We'll be talking about this from now on. And what you need to get between today and tomorrow is what I like to say is kind of a conceptual understanding of it. I mean, there's a formula we've got to use today, and it's one of the ugliest formulas in terms of the order of operations to plug numbers in. But again, we have computers that kind of take care of this ultimately. But I'm very interested that you get the concept, like what is this thing? Standard deviation. So let's just slow down for a second and think about those two words. Standard, that just really means typical. And I've got a kind of a PowerPoint we'll look at in a second that'll give you a little more of an example for this, but typical. And then you understand what deviation is. Like I bet you are, well, deviants in some regard. If you think of like, what do people do? What do people think? You probably have a few things where you deviate from that. Of course, there's weird things like you kill people or whatever. But we all, well, we vary from one, and that's what this class is really all about. We have varying opinions, we have varying whatever levels of glucose in our body and so forth, and so we deviate from those things. Well, in my case, my dad has high cholesterol, so I decided I really don't care, I'm not going to check. And so, a couple of years ago I thought, well, I should finally check. I'll see what my cholesterol level is. Well, and I'm a deviant, like mine's really high too. It's something you inherit, and so the doctor wants to give me blood thinners and so forth, but that's the idea. There is there is an average of, well, everything we've talked about, pulse and temperature and all kinds of things. There's kind of an average that people have of all kinds of measurements in your body, and based on that average, mine's higher. Does that make sense? This is the basic idea. Mine's higher. There is a standard, and I deviate from it. I'm not this, and if you think about it, doesn't everybody deviate from it? Does anybody actually have the average height, the average weight, the average strength, the average IQ? Does anybody have the average? I mean, it's pretty rare, right? We all deviate. Now, if you deviate, there's above and below. In my case, it'd been awesome if my cholesterol level was below, right? Because then it's like, sweet, give me something fat to eat. Mine's kind of high though. I deviate high. Now, does it make sense, however, that there's high deviation that's no big deal? Let's say the average is 150 and I was 151. That's a little high, but who cares, right? Because I only deviated by 1. I was off from the average of 150 by 1. And it's positive 1 because I was above it. Does it make sense if you had 149, you would also deviate, but you'd be 1 off, but you'd be 1 below? Does it make sense that might be no big deal? Yeah, who cares? But what if it was 3? What if my cholesterol level was 250? So the average is 150, and mine's 250. Well, now I deviate by 100. Maybe that's a big deal now. Does that make sense? And so that's the idea here. So if we have an average, what is it typical to deviate from that average? Because nobody has the average. Everybody deviates from it. But what's typical to deviate from that? So maybe I'll use the word kind of typical variation. What's typical to vary? So let's just play with that example for a minute. Let's say that what does that symbol mean? I've only showed you that once. Good job. That's the mean, but that's actually the population mean. Now you can probably appreciate that's almost impossible. Like, how could you actually know that the population mean, like, has everybody that's ever lived been tested for their cholesterol level? that's kind of not true just by the very fact that you even write it down. But again, we're just sort of playing around here. So let's say that the mean is 150. Now, of course, where did that come from? Well, didn't that come from in the language we discussed recently of, well, they tested a bunch of people. And so, you know, here's the X's. So maybe somebody came in and they were 140, and then somebody came in and they were 165, and then somebody was 132, and then somebody was 180. And then I'll say, you know, kind of dot, dot, dot. And maybe this is a really important one, and this particular one kind of is, because if people are too high in cholesterol, they're probably going to die of a heart attack. And so it's something doctors want to check into that. This isn't like a no big deal kind of a number for health. And so does it make sense if the average is 150, then wouldn't the individual people that got measured have, you know, values that are below that and then values that are above that, and that's why it averaged to 150? That makes sense, right? But do you see that those people each deviate from that? So how much did this person deviate? And by the way, standard deviation, deviate from what? The key is from the mean, from the average. So how much did that person right there, how much did they deviate from the mean? Yeah, they're 10 off, but do you agree they're actually negative 10s, showing that they're actually below by 10, not above by 10? So there are negative numbers here, something we got to be able to deal with. And in this case, that's good, right? Yeah, you're below the average. Okay, good, you're fine, get out of here, you know, go live your life. What's this person's deviation? 15 plus 15. So you actually have to subtract to figure that out, but which way do you subtract? Do you go 165 minus 150, or do you go 150 minus 165? Yeah, does it make sense you're actually taking the X's? And remember, X's stands for a variable. In other words, each person has a different answer, and you're subtracting that. You're subtracting the mean from that. So 160 minus 150 is 15. I'll write a plus sign there, but we typically are lazy and just leave it off if it's a plus sign, right? And then 132 minus 150 actually comes out a negative number, and then 180 minus 150 comes out a positive number. So isn't that the list of the deviations from the mean? And so the issue here is kind of what is it typical to vary? And the reason this is important is because it kind of tells you whether, you know, if I come in and I'm 250, maybe just at a glance here, you can see that if I'm 250, I'm 100. Like these people deviated by, well, reasonably small numbers, 10 and 15 and 18 and 30. And then suddenly I walk in the door and I'm like plus 100. Does it make sense that you got to know what it's typical to deviate before you can decide, like I even deviate from the deviates, right? Like everybody deviates, but I'm deviating too much. So this is how you decide when somebody's not doing good. Now, again, you have a feel for this with temperature. So as an example for temperature, let's say the mean, let's switch gears to temperature. Let's say the mean temperature, isn't this right, like 98.7 or 98.6 degrees? Isn't that kind of what you have in your mind? We've talked about this a little bit. And let's say that the standard deviation, and unfortunately there is a symbol for this. This is one of them. This is the Greek letter sigma. And again, you don't have to memorize this. I'm going to give you a note sheet. I'm going to give it to you today that kind of lists all of these symbols. Let's say that standard deviation, just to keep it easy for us, we'll say, no, let's make it a little hard. Let's say it's 1.2 degrees. In other words, and doesn't that feel about right? So if we took your temperature, is it going to be 98.7? The answer is no, but isn't it going to be pretty close to that? Do you agree that the typical variation, if I was to kind of say 7.2. Does that feel wrong to you? Like if you're sick, what's your temperature? What's your high temperature? Typically, what kind of temperatures do you get if you're sick? Yeah, like 101, 102, but it's not like 115, right? Nobody's sick and they're 115 because you just burn up and die. So the standard deviation, it's not typical to vary from that by 7. If we took your temperature right now, 98 plus 7 is like 105. You're not 105. If you're 105, you are sick. Like you're not here right now. You're actually probably in a bath of ice, because when you get up to 105, it starts to get a little dangerous, right? So does it make sense that is not the typical variation, 7.2 degrees? So it's probably something, and if you want to, you could get your phone out right now and maybe figure that out. It's probably something more like 1 degree. And maybe that's even high. Maybe it's only 1.2. So then, does it make sense then that it would be typical to be 98.7 plus 1.2? That would be typical. What does that get us to? 99.9. And again, I'm making up 1.2. I actually don't know. Frankly, now that I did that, it actually sounds too high. I don't know if you feel the same way, but so this would be kind of like the high. And then if I went 98.7 minus 1.2, that puts us at 97.5. So then the range, if you're a doctor and you kind of knew then, thanks to these statistics, that that's kind of the typical range, and somebody came into you and they're like, oh, I feel really terrible. Like that's one of the things they do right off the bat is take your temperature. Does it make sense if you fell inside there? They'd be like, oh, that's normal. And they would like wipe that off as like one of the problems. And then they might check your blood pressure and some other things about you. But does it make sense if the typical variation is 1.2 degrees, then that means everybody hangs out between 97.5 and 99.9? We'd say that's pretty normal. Now, if I walk in and I'm like 102, then that's why they'd say, hey, dude, that's kind of high. You're like outside of what's typical to vary. So that's a very small standard deviation. So this is actually how you do the statistics. That's how you determine whether somebody is sick. You can't just take the average. It's also what's usual to vary from that, because everybody varies from that. Is it usual to vary by a lot or a little? So maybe up here in the case of cholesterol, I think that's how you spell cholesterol. I'll just pretend I know when I have no idea. Let's say it's actually typical to vary by a lot more. So when you measure people's cholesterol, people don't get 150, 151, 149. Well, they get numbers like this, like big variations. You get lots of variations, big numbers down there. So if that's the case, 150 minus 30 would be 120. 150 plus 30 would be 180. So then maybe that's the typical range. So the standard deviation is much higher. So again, same thing. I go to the doctor, they take that measurement of me. If I'm inside that range, then they're like, okay, you're fine. Now, if I'm at 180, they might say, it's actually at the upper end, but you're fine, get out of here. But if I come in and I'm 250, then they're going to say, wow, you're like way out of the normal range and you're high, and that's the dangerous side. And so, let's watch you. Start eating differently, start exercising, start taking drugs, whatever. I mean, they're going to tell me to do something, right? So I don't die of a heart attack. But does it make sense you can't determine whether I'm in trouble unless you understand what it's typical to vary? Does it make sense if the standard deviation here was suddenly 130? Now, if I'm 250, all of a sudden it's like, that's okay. All of a sudden, you see what I'm saying? So just knowing the average is not enough. You have to kind of know what's typical to vary from that, because there's variation. Everybody has a different temperature. Everybody has different cholesterol. Everybody has a different glucose level. So the problem with one number to represent everybody, if we say, hey, your temperature is supposed to be 98.7, what do you do when people aren't? Because they're not. Do you sound the alarm, or is that Okay, well, you kind of have to know what's typical to vary from that. Does that concept make sense? Okay, so let's actually figure out how to calculate this thing. Like, how do you figure out what's typical to vary? So I'm going to post that. Let's see, I don't want to leave the meeting. That's not what I want to do. So I will post those notes. And now let's see if we can look and also post this PowerPoint. Unfortunately, the calculation for this is kind of painful. So you're going to probably need to refer to this. This is one of those places, if you read in the book, and Tisha noticed, for instance, yesterday, she was one of the ones that told me that, hey, there's a question about standard deviation in your assignment. And she started reading the book and like, oh, okay, I'll figure out how to do that. And it was like pretty overwhelming. She said, yeah, like trying to make sense of it. It was painful.
It is, but it's doable. You really have to like pay attention.
Yeah, and I compliment the two of you for like, this is what I told you before. You will pass this class in one pass, but you got to be on it. You know, like you got to try stuff. You got to look ahead. You got to do all the assignment. You got to ask questions, and that takes time. I hope you have enough time to devote to this. So I compliment the two of you because you're both thinking ahead and asking questions, and that's really good. Okay, so the title of 3.1 is wait, we're not in 3.1. What are we doing here? The title of 3.2 is how can you measure the spread of data, the range. So a second ago, I said the spread of temperatures was, what did I say, 90, I forgot, 97.5 up to 99.9 or something like that. That was the spread, that was typical. And notice it says quantitative data, because it's really hard to do this for colors. If we said, you know, what's the difference between blue and red? It's, I don't know, it's like we can't subtract them. We had to subtract a second ago. So this only works for numbers. Okay, how do I get rid of all these dumb controls so they're not in the way? Andrea's with us, good deal. All right, that's not going to work. Let's see if this will get, nope. Okay, so look at these two neighborhoods. So this is just a good simple example. So here's houses in one neighborhood. And so this is the houses that are for sale in the Orchard Hill neighborhood. Now, at a glance, what do you notice about those prices? Yeah, they're all like around each other until suddenly at the end, there's some expensive house, right? So 5 houses for sale, 4 are, well, they're not the same, but they're kind of at least in the same neighborhood. And then suddenly there's one that's like more than twice as expensive as all the rest of them. Whereas look at this neighborhood. So this other neighborhood you're looking at also has houses for sale. And again, notice they're not in order, but notice they're all kind of around each other. Now, are they exactly the same? No, one of them is 204,000 and one's you know, 227. So it's like they vary, but notice there isn't one weird house in that neighborhood. Does that make sense? Now, interestingly, we like to use the mean. In other words, if we want one number, we already studied this in 3.1, if we'd like one number to represent all of them, and again, I'm keeping it simple, you don't really need a mean when there's only 5 houses because you can actually stare at that many numbers, right? You need it when there's 50 houses because then you're just overwhelmed with numbers. We'd like to use the mean, but do you agree that 452 is going to screw up the mean in that other neighborhood, that first one, because it's kind of high? It's going to skew the mean kind of high. Now, in the end, Orchard Hill has a whole bunch of low-priced houses and then one really expensive house, whereas River District has houses that are quite a bit more expensive than the other neighborhood, but they're all about the same. So it looks like River District is nicer, doesn't it, overall? So we'd like to use the mean, but we're a little worried about 452 because it's going to kind of screw that up. So don't take the time to do that. I mean, you can if you want to, but find the mean for each neighborhood. Of course, we know how to do that. If I just add them up and divide by 5. So if I did that for Orchard Hill, you could check my work here if you want. You get $201,000, $202,000. If you do it for River District, notice you get almost the same answer. So the average price of those two neighborhoods is about the same. If we use the mean to represent them, does it make sense those two neighborhoods look the same? But since you can stare at the numbers up there, are they really the same? They're not, and that's the problem with the mean. If you only use the mean to represent, all the players on the football team, you might be losing something about how the neighborhood works. And so if I looked only at those two numbers, I'd say, oh yeah, those two neighborhoods are about the same. It costs like $200,000 to buy a house in that neighborhood. But again, you look at Orchard Hill and you're like, no, it doesn't. It costs like 100 to 150 for a house, and then we're not going to buy that one expensive house. Whereas River District, 201,000, 202,000 is actually about right. That's kind of is the price of the houses in that neighborhood, right? So you see how something is lost? Remember, if we have 92 football players, we can't stare at that many, so we get an average and we sort of throw the numbers away and we just hang on to that one number that represents all of them. But you see how something can be lost from that? This is what standard deviation is going to allow us to understand. Now, so by itself, the mean leaves out important information. So range, here's the concept. One way to measure the spread of the data is to calculate the range. In other words, the biggest price minus the lowest price. Maximum minus minimum. But does it make sense that $457,000 house is going to make it a really large range in that neighborhood? And that would be some indication that, wow, there's a big difference in prices in that neighborhood. And that's really affected by outliers, really high expensive houses. And that's actually a really simple calculation. If we just went expensive house minus cheap house, that's a really simple calculation. But here's what standard deviation is. And this isn't gonna be how we calculate this, but this is the concept behind it. So each value has an associated deviation from the mean. Now that's a complicated statement, but it's very important to me that you understand it. In other words, how far is each house away from the mean? Well, isn't that what I just did a second ago with cholesterol and so forth? It's like how far the guy that had 140, how far was he from the mean? And we said he was -10. Like that's the deviation. He deviated by 10 and it was down, negative. So the language can be complicated, but the concept isn't terrible. Is it that kind of the formula we used? We took the individual score of each person and we subtracted the mean from it, not the other way around. So if it's positive, then it's going to be above the mean, right? Because if we subtract the mean from it, and it's bigger than that, we'll get a positive number. It'll be negative if it's below it. So that's kind of important. If I get a negative there, it means I'm below the mean. Now let's actually go kind of calculate this for Orchard Hill. So we said the mean for that neighborhood was $201,800. And so does it make sense that Orchard Hill here is below the mean? So do this on your calculator really quick. If I do this formula and I go 125, and notice to save space, I put K for 000. So take 125,000 minus 201,800. What do you get? It's like 75 or 76,000, something like that. But importantly, what's in front of that number? A negative. So that means it's basically $76,000 below the mean. It's under the average price for the other house. I mean, it's kind of cool to know, right? It's like, oh, that house is way below the average. That's awesome. Well, isn't every one of 1, 2, 3, 4, all 4 of these are going to have negative standard deviations, negative deviations, if you will, from this mean, because they're all below it, whereas this last one's going to have a massive deviation positive above it, right? So let's actually go kind of write all those down. Notice River District, its And again, both of these means are approximately the same. Well, notice these deviations right here are going to be much smaller numbers, aren't they? So let's actually go calculate the average deviation for the mean for each neighborhood. So this is what you just did a second ago. Isn't this the number that you just got? You took 125 and you subtracted, I forgot, 201,100. Isn't that what you got on your calculator? Negative 76,800. And now let's do it again for 132. 132 minus 21,800, you get negative 69,000 and so forth. And notice this last one, 250. And it's positive. So it's like, wow, that house is $250,000 over the price, over the average price of a house in that neighborhood. Wow, that is huge. So you get some rather large deviations. Now, anybody taken algebra and knows what that bar means around it? What does that bar mean? Actually, what happened to the numbers? Notice the numbers are exactly the same, but what happened to the numbers right here? Yeah, notice the negative sign is gone for these. In other words, in the end, in English, you would typically not tell somebody this house is negative 76,000 from the mean. You just say it in English. You'd say it's 76,000 below. You'd use the word below instead of a negative, right? And so these are the deviations without considering what direction they went. And so then what we're calculating then is the average of those deviations. And I would like you to do this really quick. Take those 5 numbers and add them all up, all the deviations. You're adding up the deviations and you're finding the average of them. So you're going to add those 5 numbers up and divide by 5. And see if you don't get 100,000, 80 bucks. So in other words, in that neighborhood, although the average was like $202,000 for a house, it was actually typical to deviate from that by an average of $100,000. Wow. So you're saying in that neighborhood, it wouldn't be weird to be 200 plus 100, in other words, 300,000, or 200 minus 100, or 100,000. In other words, you're kind of getting $100,000 to $300,000 houses in the neighborhood. That's a really big typical deviation. It's a big deviation, lots of deviation in that neighborhood. And that's the idea. From the original list, we saw that we had low numbers and really high numbers. And so there was pretty big range there, scattered all over the place. And so what we found here is the average deviation. It's a large deviation from the mean. So for Orchard Hill, we had a mean of approximately 200,000 and a standard deviation approximately 100,000. Does it make sense? Even if those two numbers came from 500 houses for sale, totally overwhelming numbers everywhere, and I got rid of all 500 numbers and I just had this. If you understand what these two things mean, does that give you a sense of kind of the price of the houses in the neighborhood? This is the average, so there'd be lots of houses around this, but then it was pretty typical to be 100 higher and 100 lower. Now, interestingly, when you look back at the list over here of the deviations, notice 76, 69, 57, 45, those are the deviations. Those are all way less than 100,000, but then this cat, 250 over. So the average of these 5 numbers came out 100,000, but even that 100,000 kind of is a little deceptive. Like you would never know that there'd be a $452,000 house for sale here. It does not mean that every single house is between 100 and 300. Does that make sense? It does not mean every single house is in there, but that means that's kind of what's typical. Now let's do this for the other neighborhood. So you don't have to type this one, but let's just look at it. So again, this house, what was it, 202,000? I forgot. Around 202,000, I forget. But notice this neighborhood, when you subtract, you get much smaller deviations. Notice this one was almost exactly the average price. Do you see how that just at a glance, these deviations are much smaller than they were in the other neighborhood? And so when you take the average in that neighborhood, notice the average deviation is only 15,000. So the averages were still the same. And if that's all you had, you'd say, oh, those are the same neighborhood. But then when you add one more number to this, and that's roughly 15,000. Does it make sense, like what a radical difference knowing those two numbers makes? Knowing this number says, oh yeah, all the houses here are really close to 200,000. So I have a sense of what's going on there. Again, it doesn't mean they're exactly 215,000. There isn't any of them that are 215,000. Is it telling you the price? It just means on average, they're about 15,000 off of that. So they're all pretty tightly spaced. They're all about the same kind of house. But even then you have some that are, you know, quite a bit above that. Isn't that 24,000 over that is almost two of those standard deviations away. And then this person's price was almost like right on the average. This house, 13,000, that almost was exactly the deviation that you would expect. It's pretty close, but it doesn't tell the whole story. Doesn't tell you exactly how much each price is. But basically the concept is, whoa, this neighborhood, this is the average and the houses are way up and down from that. This neighborhood, same average, but they're not that far off of that. So do you see how two numbers, if you have both of these numbers, that actually kind of tells you what's going on from the original list. So you can't really just have one number that represents lots of numbers. But if you have two, that actually tells the story pretty well. Now I want to take just a quick pause and look at the Dallas Cowboys here for just a second, just to kind of give you a sense of this. So again, this is the lab we were working on Monday, and you know, here's the Dallas Cowboys, and we saw that the range here, 330 for the heaviest player, 185 for the lightest player. And so there's a few things we can do. So I'm going to go over here and find the mean. I'm going to cheat and use this machine to do this. So equals average. And then instead of typing this, I'm just going to grab all of those. So we said this the other day, right? The average weight for a player on that team is 245. And in this case, there's 92 numbers, and so I can't even stare at all of them, right? This is why we do this. But again, does that mean every player on the team is 245? No, it means there's lots of players that weigh less than that, lots of players that weigh more than that. But does it make sense from just this number? We don't know, you know, how much variation is there? Like, does that mean all the players are right around this? And are the players like from 240 to 250? Well, again, we look over here and it's like, wow, 185, that's way below that. And 330, that's way above that. So let me calculate the standard deviation. So let's see, what's the command for this? Standard deviation. So again, I'm cheating to do this. Yeah, so both in your graphing calculator and in Excel, there's a cheat way to do this. And when I show you in a second how to do this by hand, you're gonna be like, oh my God, how much is Excel? I don't care if it's $5,000, I'm gonna buy it. I am gonna ask you on a test for a small list to do it by hand. I want you to understand the concept. We aren't gonna actually do that very much in this class. For the most part, we're gonna let machines take care of it. The important thing in the real world is actually not to be able to make the calculations by hand. It's actually to understand the answer that you got. So for now, we're just sort of cheating. And to keep it simple, I'm going to round that off. Let's see, which one is that? Increase the decimal. I want to decrease it. Would you agree 43.8 is going to round to 44? So my point is, if you stare at those two numbers for the Dallas Cowboys, does that give you a sense now of what's going on? Oh, so it's typical to vary from 245 by 44 pounds, not 4 pounds. That would mean everybody weighs right around 245. But you see how, in a sense, that kind of helps you understand the original list now? Exactly. So in other words, it's really typical to be, let's see, 245 plus 44 is 289. That'd be the top end, right? And then 245 minus 44 would be 201. Would you agree that's lots of players are going to be in there? That's what's typical. So if your weight was in there, it'd be like, yeah, of course. Like, we're not worried about you. If this is a doctor's office, if you're in that range, get out of here. You're fine, right? That's normal. That's exactly what you'd expect. But does that take care of everybody? Are all the players on the team there? No. What if we went plus or minus, do this on your calculator. What if we went plus or minus 2 standard deviations? So add 2 44s to 245 and subtract 2 44s. Can I give us one of them since I don't know the answer?
You said to add 244?
Yeah.
333.
Did you say 333?
Yeah.
Okay. So then if somebody gets this wrong, who cares? Paloma, what's the bottom one? If you take 245 minus 2 44s, what do you get?
Wait, 244 minus 44. Oh, 157. Yeah.
What is it? 1 what?
157.
57? Now, does that capture all the players on the team? Notice right here, you have the minimum and the maximum. Did that capture everybody? It did. The lightest player was 185. So they're higher than this. The heaviest player was 330. They're less than this. That actually captured everybody on the team. As a rule of thumb, we'll be talking about this today and the next day. As a rule of thumb, if you're within 2 typical deviations from the mean, the doctor is going to say, get out of here, you're fine. That's typical. If you're outside of that, now all of a sudden we're worried about you. So if there was a player on this team that was 350 pounds, it'd be like, wow, that's unusual. If you're outside of 2 standard deviations from the mean, that means you're unusual. If a player was in the NFL on this team and they weighed less than 157, wow, you're really light for an NFL player. So this does not capture everybody, but typically this does. This usually captures everybody. That's why standard deviation is so powerful. In other words, just these 2 numbers, just 245 and 44, actually did kind of allow us to recreate the whole team, even though it might be lost. You see how we kind of have a sense of it? But you got to understand something that you wouldn't understand until today, that most players are going to be in here. And it actually turns out that 68%, I'll show you this more on Thursday because we won't have time today, but 68% of the players you could actually predict would be in this range. And if you make the range even wider, then it goes up to 95%. This is predictable. It's like every case, cholesterol, football players. Now, 95% is a lot, but 5% is still 1 out of 20. So even in a room this size, there's almost 20 of us in here. One of us would kind of still be outside of that range. Now, in the case of the football team, everybody was inside there. But this is why mean and standard deviation together actually tell you a lot about the original group. Now, let's go back. Now, I want to show you how this is actually calculated. Notice that as a gnarly formula. We've been working on, and we're going to continue to work on here pretty quick, probably talk for 15 more minutes about this. I'd like to make one calculation of the actual standard deviation. That's a really ugly formula. And remember, I just cheated and Excel did it for me. So it's like I didn't even have to do that. I got the right answer. And I did it for 92 football players. By hand, that would have taken me like 2 hours to do that. So it's pretty cool we live in this generation. I mean, people for hundreds of years did this, but they had to do it by hand, not even have a calculator. So the fact that we have machines that will do this automatically is really cool. Now, this formula is really complicated. Would you agree we got an order of operations problem here? Do you see there's a subtraction here. There's an exponent. What's that symbol? That's divide. And from the other day, what's this symbol? Sigma. What does it mean to do? It means sum, or to add them all up. So we've got a bunch of adding to do because of this. We got some subtracting to do. We got some dividing to do. We got some exponents, and then we got a square root. And you got to do that in the right order, or you get this question wrong. And so that's pretty daunting, right? Like you got to really understand order of operations pretty well for that. So as it turns out, then in order for this to work, that X bar symbol was one of our symbols for the mean. So we got to find that. And then in the order of operation, we got to find the deviation of each value from the mean. Isn't that subtraction right there? In the order of operations, isn't parentheses first? And so does it make sense that subtraction right there would be the first thing we do? So we got to take every score, as you just did a second ago, we got to take every score and subtract it from the mean. That's the first thing we have to do. Not just one, we got to do it for every single number. We just did that for Orchard Hill. We subtracted each one of them and got an answer for all of those. So that's first in the order of operations, is parentheses. What's next in the order of operations? Exponents. That exponent right there, we're going to have to take those answers that we subtract and then square them. So each answer, square it. And remember, giant division signs are like a parenthesis. In other words, we can't do this division until we finish what's on top. And so once we square all those answers, then we've got to add them all together. That'll be the next thing we have to do. Add up all of those big squared numbers we just got. Then we can actually divide by n. And once we have that answer, then finally we can do that last step, which is to square root it. That says find the square root of that result. That's really a daunting process. And I am going to ask you on a test to do this for a small bunch of data, like, well, the houses. There's like 5 houses or something like that. So let's step through this really quick for one of those examples. Again, you can look at this later. So here's 7 metabolic rates. Metabolic rate is how many calories per hour you burn. Does it make sense people vary in that? Some people burn calories like crazy and have to eat like crazy. Other people don't burn calories very fast. Does it make sense there'd be variation in that? So somebody measures that, some health nerd measures that for 7 people, and notice there's quite a bit of variation. This person was only 1362 calories in 24 hours. That was their natural metabolic rate, whereas this person burned almost 1900 calories in 24 hours. That could be just body type. So let's find, I'll go through this pretty fast. Oops. Let's find the mean. Well, you know how to do that. You add them all up and divide by 7. So if I add all those up on the top, I get 11,200. I divide by 7, and you get an average of 1,600. A mean, X bar, a mean. Why is that X bar? Why is that symbol X bar and not the other option? Why is that the symbol there? It's a sample. Is that all the men in the world? 7? Is one 7? No, it's a sample mean. So it's just 7. So it makes sense why that symbol would be used. Now, at a glance, does 1600 look correct if you look up here? Notice you got 1800, 1600 is below that. You got 1300, 1600 is above that. This person's almost right on the average. But that does kind of feel right, doesn't it? Like check that on the test. It would not be hard on the test. All you got to do is type 1362 in your calculator and the 6 accidentally doesn't show up. So you actually type 132. Does it make sense? That's going to totally screw up the answer. Maybe you'll notice. Maybe you'll notice it. Because you should see that this average, sure enough, is kind of in the middle of this group. Okay, so we got our average. Now you sort of have no choice but to, well, what did that formula say? The first thing we had to do is subtract each number from that mean. So I took the first person, 1792 minus 1600, 192. What does 192 mean? That means they're 192 above the average. Then the next person, 1666, they're 66 above the average. This person, 1362 minus 1600, notice they're 238 below the average. Wow, that's a big deviation. Are you seeing deviation happening here? That's what we're calculating, is how much deviation is there. This person was almost right on, and so their deviation was only 14, but again, 14 above, right? And so on and so forth. And so we got all those deviations. And I took the formula away, but what the second step we had to do was square them. And so notice I took that 192 there and I squared it, and notice that became a humongous number. And 66 squared, 40, and you can check one of these if you want to. I'd like you to do this one on your calculator really quick. Type -238 and then square it. Most of you are not going to get that answer, so I want you to stare at why did that happen? This is really important because this will screw everything up. Did you get 56,644?
Negative.
You got a negative. Do you see that? This is very important in your calculator. This kind of it's actually kind of a mistake in my opinion in your calculator. If you type -238 and you say squared, your calculator knows the order of operations, and it actually sees that negative sign as kind of like a multiplication, like it's being applied to the number like a multiply sign, and therefore it actually does that first. It says, I know the order of operations. I'm supposed to square first, and so it squares that number, and then it applies the negative later. But isn't a negative times a negative a positive?
Yeah.
So it's like that number should be positive. And notice up there, it is positive. What did I actually type here though instead? Instead of -238 squared, I put parentheses around it. Do you see that? So you got two choices. If you want to square this number, you either actually have to put a parenthesis around it, telling the calculator, dude, I want you to do that first and then square it later, and then you'll get it right. Or you just know in your head that a negative times a negative is a positive, so why not just leave it off? Does that make sense? Either one of those is fine, but you got to be really careful if you're squaring a negative number because you might get it wrong. Notice what squaring does. It actually cleanses these numbers of all the negative signs. Does it make sense? You should never have a negative number over here, because whether you square a positive number or a negative. And by the way, a second ago, we took the absolute value. In other words, we found the average of the deviations. We had to have positive numbers for that. And so we just got rid of the negative signs. Well, actually squaring and square rooting, that will get rid of the negative signs. That's why this process is what it is. So the second step was I squared all of those numbers. Let's back up. Second process is I squared all of those numbers. And then the third process is now I got to add up all those big squared numbers. And then the fourth will be to divide by however many numbers are on the list. And then last, take the square root. Like those are the steps I got to follow. Let's see, what is there? There's 1 for subtraction, 2 for squared, 3 for add, 4 for divide, 5 for square root. I got 5 steps I got to do here to get the answer to this thing. Thank God there's machines that do this automatically. So third step is I take all of those numbers and I add them all up, and there's that answer, 214,870. And so if you take that 2114,870 and you divide by 7, you get this number. And you're welcome to kind of punch any of that into your calculator and double check it if you want to. We'll do an example together in a second. And then lastly, you take the square root of that answer. Bam, 175. That's the standard deviation here. So again, why is this powerful? If you look back at the original list of metabolic rates over here, basically what that's saying is the average was 1600, but that didn't really tell the tale because the numbers were all over the place. What was it typical to vary from? 1600, it was typical to vary by 175 calories. So if I take 1600 plus 175, don't I get 1775? So that's the kind of variation you'd see. Does it make sense? This list over here could have been a whole bunch of numbers that were extremely close to 1600, like 1601, 1603, 1595, numbers that were really close. But are these really close? No, they're 175 off that. There's a lot more variation in metabolic rate among people. Do you see why that number is kind of cool to know, even though its calculation is kind of a pain in the butt? So that sigma, that standard deviation, tells you something about the spread of the data, how far they are apart. Does it make sense if the standard deviation was nothing, then that means every single person's the same? So it's like, how many eyes do you have? 2. How many do you have? 2. How many do you have? 2. And then we said, okay, the average number of eyes is 2 in this room. How much deviation is there from that? None. Everybody has 2 eyes. There isn't deviation in that particular measurement for people. So the calculation we just made is for a population standard deviation, which actually means you know everybody. Now, a second ago, we only checked with 7 dudes, right? Did we know everybody? That's just 7 people. Does it make sense if you only check with 7 people, then there could be other people out there that have wildly different scores that we never checked with, right? So there is a calculation that is made to account for the fact that there might be more variation out there that we didn't check. Notice it's the same formula, but what's different about it? Yeah, instead of dividing by 7, you'd be dividing by 7 minus 1, you'd be dividing by 6. And what that'll do is make the number a little bit bigger. It'll make the standard deviation a little higher to account for all the other people you might not have checked with. That's kind of the idea. If you only check a sample, then that means your data is kind of sketchy, you're not really sure. Okay, let's stop at that. And so what we'll do on Thursday, because I actually don't have, I have a little bit more to show you about this 68-95% thing. There's something cool there, and actually that last slide was talking about it. It's called the empirical rule. And so we'll talk about that, and then we'll just practice this. Like if I give you a list of some numbers, can you make this calculation slowly? I mean, you have to make a chart. It's going to take a whole piece of paper. You got to write everything down. You got to be really careful not to do something stupid. But I'm also going to show you on your calculator how to get your calculator to produce the answer too, so you can at least check yourself. Because with that many steps and that many calculator button pushes, there is no way all of us in this class are not going to make some mistake, right? And again, I'm just as likely as you are to make that dumb mistake. So all we need to do on Thursday is just kind of practice this a little bit. Make sure we know how to get the calculator to do it and so forth. And then we'll be living happily ever after. So as I said, I'm going to post this so you can actually look at that calculation, because you have one example now of a good step-by-step list. I would highly encourage you to go stare at that PowerPoint and just like try it yourself a little bit, punch a few buttons and kind of be like, oh yeah, I can get that. I want to hand you something. I want to hand you the note sheet now for this first test. And then we're going to kind of go Actually, I think this might be faster. Why don't you just come get one of each of these? Probably faster if you guys just hop up really quick and do that. So I just want you to stare at something on that note sheet. I'm going to pull this up really quick. And you might notice the label on the top of that. I think it says this is your chapter 2 through 4 test notes. I've mentioned before that I don't expect you to memorize stuff like formulas. There's no point in memorizing a formula. We have cell phones, right? I can just say, Siri, what's the formula for standard deviation? And I'll have it in front of me in 2 seconds. What I want you to be able to do is think, reason. Where'd you go? I give. Why are you disappearing? So notice things that we've learned recently. Class width, that was maximum minus minimum divided by number of classes, and then you round that up to match the data. That was a formula we needed to make a bar graph, right? So that's on there. And here's something we're going to talk about later in the week, but check out these formulas here. So X bar, notice down below, I made this list of some of the symbols right there because you will memorize these kind of by accident, if you will, but that's kind of helpful. So notice down there, X bar is the sample mean. So if you see that, you're like, oh, what was that again? And then there's that sigma symbol. What does that mean? Oh, sum. Yeah, that means add them all up. That's what that means. And so isn't this the formula for the mean? If you add up all the X's and then divide by N, what was N again? Oh, that was the number of the data points. Isn't that the neat, pithy little formula for how you find the mean? I will ask you that on a test for a small number of data points. But then what we just studied right here, stare at that. Now I had some people last term talk me into 1, 2, 3, 4, 5 here, because that is such a complicated order of operations problem. And so I thought, I think you're right. And so I put 1, 2, 3, 4, 5 in there to actually show you the steps a little more clearly, because that's even if you know order of operations, you got to know it really well there. So stare at that. What is that saying? It's saying first, do these subtractions. And again, you should recognize that because parentheses are first, right? And then second, what's after parentheses? Exponents. And so you square all of those. And then third, this is a little less obvious, then you actually add all those numbers up. And again, that's because giant division signs are like parentheses. In other words, I can't proceed to division since up here, I've got to finish this first. So add all of those up. And then fourth, divide, I'm pointing at that division sign, divide by n, and then finally fifth, take the square root of that. Isn't that what we just did a second ago? So on a test, I am going to ask you by hand to do this, but I'm also going to show you on your calculator how to check it. I would love to see a note on the test that says, I know the right answer is 7.2. Somehow I got 8.4 and I don't know what I did wrong. Like, that's cool. In the real world, nobody ever does this by hand. I think it's just important to do it once and kind of show you understand the logic behind it. But again, as complicated as this formula really is, if you square something and square root it, all you're really doing is getting rid of the negative signs. That's why it's there. Because if you take -2 and add it to +2, that turns into 0. So you don't want to add negative and positive numbers. You basically got to change them all to positive like we did by hand a second ago. So this is a really weird, complicated formula. But you're really just adding up all the numbers and dividing. Isn't that an average? And the squaring and square rooting just gets rid of the negative signs. Because in the end, I just care about what is the deviation. The standard deviation, I don't really care, is that up or down. And so that's a formula that'll be sitting there on the next test. And you should be thinking, thank God, because I wouldn't want to have to memorize that. If I did make you memorize it, if you were smart, you'd be standing outside that door looking at it. And then you'd come in for the test. And as soon as they hand you the paper, you'd quickly write it down. And so I basically succeeded in making you memorize it for 10 seconds, right? That's why I think it has no point. The real problem is, do you know what to do with it? Do you know how to use it? Now, of course, there's a bunch of other stuff on this page that we haven't talked about yet, right? That's coming. We'll get to that. We'll get to that a little bit later. But this will be everything that you need to know for the next test. So keep this. I put hole punches in it. Yeah, you'll have this in front of you for the test. Now, also, I'd say this again, like if there's anything else that you wish was on this, I don't want you to, the test will not be open note, because then you can just kind of copy an example and actually get problems right and not even know what you're doing. Remember, I want you to actually be able to do something in a job someplace that actually gets you a raise. I mean, that's why you're taking this class. So if you just copy an example, that isn't actually showing that you actually understand something. But what's on here is stuff that smacks of memorization. So if you're doing something and you think, man, it'd be nice to have that on that sheet, make your case and I'll add it to it. Like this is a working document. I added those 1, 2s, and 3s and 4s because of people last term. So we'll talk about this empirical rule thing next time. Notice the 68% and the 95% that I mentioned a minute ago. I'll explain that to you a little bit more clearly.
The
Shelley.
difference between X's and then the X's with a little I on the bottom. Is it the same thing, or is it?
Where are you seeing that?
So it's not, the XI isn't on there. I'm just wondering, because I see it in the book.
Oh, yeah.
It's
Like the little X's, does it make sense for the problem we just did a minute ago? We had 7 different people. And so we could say X1 for person number 1 and X2 for person number 2 and X3 for person number 3, because they're not all the same number, right? So that's just a little subscript that allows you to say this is, you know, your X1 and your X2 and your X3. We're going to check all of your metabolic levels. And so that's a way of saying they're all X's because X is your metabolic rate, but they're not all the same. You're person number 1, you're person number 2, you're person number 3. And so that little I just kind of means which person, you know, what number are we on here? Does that make sense? Okay. Go away, stop sharing. Okay, so now we are switching gears and doing some more algebra, and the other sheet that I handed you is that algebra. So let's play with that a little bit. We've practiced a little bit the order of operations. We have not practiced enough that everybody in here is excellent at it, I would say. I wonder if you agree with that. So this sheet right here is what we did last time, where we practiced the order of operations. Wow, that didn't come through very good. That's not good. Let me see what your sheet is. Yeah, this is not the sheet you're looking at. I was going to do one example of order of operations, but it's like the formulas like didn't show up. They didn't transfer. Actually, let's do this one really quick. So this is the sheet you had the other day, except for you didn't have this on it. I actually added this. But in terms of order of operations, this is probably one of the neatest formulas that exist. I mentioned this the other day, the monthly payment formula. Let's just play with this for just a second. This is, again, a really hard order of operations problem. Now, we don't need to know this for statistics, but does it make sense? This formula affects every single one of you, and in a really profound way. I mean, you're actually in this class right now, not because you want to know math, but because you want to make a little bit more money and have a job you like, right? That's what you're really doing here. And in the end, that's going to give you some money, and that money will allow you to buy some things that you'd like to have, a car or a house. Those will be 2 things that are kind of huge. And monthly payment formula is kind of how this stuff is calculated. And again, for me personally, to be able to do this kind of by hand and actually understand it, that gives me a sense of kind of power. It's like, I feel like this is cool. I actually know how to do this myself. Most people have to go to an app on their phone or to the internet, and whatever, anything could pop out of that and they'll just write it down like they have no idea. The customer is sitting there buying the car, and then the salesman is selling the car. Neither person knows if the answer to that monthly payment is right. But it's like, I'm going to pay this for a long time. Like for a car, I might be paying this for 7 years. It's like, I'd like that to be correct. Like, I don't want to get ripped off. So let me just walk you through this. It's kind of cool. You don't have this, so if you happen to find this interesting, write that formula down. But again, could you get online and find this in 2 seconds? Yeah, that's how I found it again. I don't have this memorized. I found it online really quick. So, wow, this didn't, I got to save stuff as a PDF file because this didn't copy correctly either. I'm going to write over the top of this a little bit better. This is supposed to be like this. Okay, so let's find the monthly payment. Let's do a house instead of a car. P is the principal or the loan amount. So let's keep it simple. Let's buy a $300,000 house. Around here, unfortunately, that's not a great house. I don't even know if you could find a house for $300,000 around here. That's a terrifyingly large number. So that's the principal amount. Interest rate, R is the interest rate. Does anybody know, like, what's the interest rate to buy a house these days? It's always changing. What kind of a number is that? Is it like 12%? Is it 2%, 15%? What kind of a number is it? Anybody know?
3%?
Yeah, it's kind of like 3, 4, 5, somewhere in there. So notice it says divided by 12. So I'll say it's 4% just to keep it. Actually, that's not good. Well, that's fine. We'll do it anyway. But see, that's called an APR, an annual percentage rate. So dividing by 12 actually makes it a monthly percentage rate, because that's how you pay monthly payments, right? You pay it every single month. So my calculator says 0.04. You're welcome to do this with me. 0.04 divided by 12 is 0.00, and then 3's forever. So unfortunately, I have to round this off. I'm going to round it off to that many places. And then lastly, N is the number of payments. Does anybody know how many payments do you typically make for a house? How long does it take to pay a house off?
30 years.
Usually 30 years. Now, that's monthly though, right? So you don't make 30 payments, you make 30 times 12 payments because they're monthly. So the number of payments would be 12 times 30, which is 360. And so those are, well, aren't those the variables? Is every house cost the same? Does everybody pay the same interest? Does everybody pay the house off in 30 years? Those are variables. Those change from person to person. What's the power of algebra? Sorry that's a disaster. Whose monthly payment is that right there? That formula right there? It's kind of a trick question. I'm asking you to read my mind a little bit. Everybody in the universe. And that's not even just houses, that's cars, everything. That's every monthly payment in the world. That's kind of cool. This says take P times R. There's no such thing as P times R. There's no such thing as math with letters. When does this become math? It becomes math when you plug in all those numbers we just found. So I'm plugging in all of those numbers. There's P, there's R, so P times R, and then 1 plus R, oops, raised to the, whoa, look at that exponent, 360. That is a huge exponent. Can you imagine without that button on your calculator, multiplying something times itself 360 times? Thank God for calculators. And then all of that giant division sign is over the top of one, same exact thing, 1 plus R, I did it again, 1 plus R again, raised to 360, but on the bottom, there's also a -1. Now we're doing math. Now it's not anybody's house, anybody's car, that's your house. Now it's specific. Now you're actually doing math. This is your house. So I wonder what the monthly payment would be on a $300,000 house at 4% APR interest if you're going to pay it off in 30 years. Again, I'm going to go from, I mean, how old are you? Add 30 to that. Does that feel pretty old to you? That's how old you're going to be when you pay that house off. It's like, this is a serious calculation. Like, don't get this wrong. But do you understand order of operations well enough to get that correct? Do you see that there's tons of operations here? Do you see that we have subtraction, we have addition, we have exponents, we have division, and we have parentheses. We actually have every single order of operations there is. There's all of them: parentheses, exponents, multiply, divide, add, and subtract. There's every single one of them in this formula. The question is, can you get it right? Like, do you know order of operations well enough to get this question right? What's first? Parentheses. So like, do this a little ahead of me. Like, take the sheet I gave you and flip it over or something. So parentheses, you should almost be able to do that in your head. So parentheses are first. So I guess that would be one point zero. Dang it, why can't I have a brain? 0033. Would you agree I just completed step one? I did the parentheses. What's next in the order of operations? Exponents. Notice there's two different ones. So what does your calculator say that is? So yeah. So how do you do that in your calculator? 1.0033. See this button right here? A little upward arrow looking Zambritas, that's the exponent symbol. So hit that. Now, not everybody's calculator is going to do the same. I have a newer one, and notice it actually hopped up there to actually put the number up in the exponent visually. Some of yours will just actually put that symbol in there. Either one is fine. But every year they're always like making calculators a little better. I think if you have the 84, I think it does exactly what mine just did. That was one of the improvements of the 84. Again, stop and stagger at how long, like how are you going to do this if it isn't for that button? You literally have to take 1.033 times 1.033 times 1.00 360 times. This would be terrifying. Notice you get a surprisingly small number. Isn't that kind of weird that it came out like that? As a quick side note, watch this really quick. Remember that number was actually not 1.033. It was actually that number, wasn't it? And so what if I took that and raised it to the 360? Do I get the same answer I got before? Notice we got 3.274. It's actually 3.313. Does that matter? It actually would matter in the real world. Like, that's probably going to change the answer here. We're actually not going to get this answer right unless we use this number, but I'm just trying to show you the order of operations. So we're going to stick with the one we had, but it's like those extra decimal points that we kind of threw away, they actually changed that answer quite a bit. That's kind of interesting, isn't it? So I'm just going to call it 3.274. So again, let's update where we are. So do you agree I'm stepping carefully through the order of operations here? And it's starting to get nicer. It's starting to get reasonable, isn't it? Now remember, what's next? Do you agree I have multiplication, subtraction, and division left? Remember, this is a giant division sign, which basically means I have to complete the top and the bottom separately, and then lastly, I can do that division. So notice on the top, it's all multiplication, so I can just multiply all that together on the top. And then on the bottom, I can subtract that, and then I'll finally have a division. So on the top, I'm typing 300,000 times 0.0033 times 3.274. On the top, I got 3241.26. On the bottom, I can do that in my head. 3.27 minus 1 would be 2.27, wouldn't it? And so finally, did you get that answer right there? So you're gonna write that check how many times? 360 times. And then you're going to be your age plus 30 when you're finished and you get that paid off. That's exciting. That's an exciting day. Get yourself some cranberry juice and get your cane out, take a walk, man. It's an exciting day. All right.
At that time you'll be working base, no.
Exactly. It's like, I'm excited here. I just paid my house off. It's a huge number. Now, I would like to, maybe I'll give you extra credit for this. As I showed you a second ago, and notice the symbol I used right here. I said it's approximately equal to that. That is not what the internet would give you if you went to a website to get the answer to this, because we rounded it off. And so what I don't know the answer to this, but what I'm curious about is how much different is the right answer to this question? Like if you, for extra credit, go back and I'll show you one thing really quickly here. Remember how we said the actual answer wasn't 3 point. When we took the decimal, it wasn't really 1 point. It wasn't really 0.0033. And so this number wasn't supposed to be 3.274. It was actually supposed to be 3.31349 and so forth. So like this is not okay. Like this answer is actually off. But the question is it off by like 10 cents? And so who cares? Or is it actually off by like $2 or something like that? So for extra credit, if you want to turn it in later, I'm going to forget I asked this, but this is something I do a lot on my syllabus. I said, I'm going to give random extra credits in this class. And if you do, I forgot 2 or 3 of those at the end of this class, if you ended up with like 79% and you ask me, is there anything I can do to get a B? I'll say, yeah, remember that extra credit I gave on the 12th of January? Did you do it? And no. I mean, that's what gives me an excuse to give you the benefit of the doubt. Plus, it's just interesting. Like that's an interesting answer.
So use these numbers that we used today.
Yeah. So do this calculation again, but just don't round it off. Now let me show you a quick trick in your calculator. So here's what I did a second ago. I did 0.04 divided by 12, and that was that's our actual R, right? Do you see this little arrow right here? It says STO. That's short for store. And your calculator, I'm just picking one example here, but notice that comma right above it, it says J, and there's that parenthesis and right above it is K. So it's like has every letter of the alphabet, and that's how many places you have to store a number. So since this was R, I'm going to hit that button, store. We got a focus problem. And then where's R? Go find the letter R. Where is it on the calculator? Blurt it out. Somebody will be first to find it. Yeah, it's right above the multiplication sign. Do you see that? So how are you going to get it? Like if I hit the multiplication sign, I'm going to get multiplication. Yeah, second. See on mine, it's green and this button is green. So if I hit second and then I hit that button, basically I just said, store that number in R. And so I hit enter. And now instead of typing in 0.0033, which is actually wrong, I'm just going to type R in there because that number is now stored in there. So the question is, could you recalculate this and actually get it exactly correct to the nearest penny and get the real answer? Really quickly, because I think it's kind of cool. There's two things I just want to show you really fast. Actually, one of them is this. No, actually, let's wait and do this in a second. So I'm going to type loan. What's going on here? Share. So I'm going to do what humans do, in the real world. Does anybody calculate this stuff by hand? No, because it's like there are websites that will do it, and it's dangerous. Like even though I know my stuff, I can still hit a button wrong. Does that make sense? I'm a math teacher, so I got a good shot at getting it right. But I'm just going to go into Google and type loan calculator. Loan calculator, loan payment calculator, loan amortization calculator. I don't know. I'm just going to type loan calculator. Simple loan. I'm taking the first one. What are the variables in a loan? Notice the words they're using, principal. It's like that's a math word. Loan amount would be nice for the rest of us, but there's a little terminology here. So what's my loan amount? 300,000. Whoa, what's going on here? What's my interest? We said 4%. Notice this is kind of interesting because it's like this is supposed to be sort of meant for dummies. In other words, are we smart enough to know you're supposed to divide by 12? No, that's going to take care of it for us. That's the interest rate. Notice there's a percent sign over there, which is why I didn't type 0.04, because even that would require knowledge, right? Like you've taken some math here with us, and so you should be smart enough to understand that. But here it says, hey, there's a percent sign, so I can just type 4%. And then number of years, 30. Notice I didn't even have to calculate, that's 360 payments. So this was made to like not have to know much, right? And so calculate. What answer did we get? 1425. So it's actually off by like $7. So that's not terrible, but 7 times 360 is still like $2,000. So the answer you should get if you, in your extra credit, there it is, 1432.25. Like, I love machines. Like that's how I calculate monthly payment. I don't nerd out and do it longhand. So let me just show you one last thing. So that was your monthly payment, right? As I asked you a second ago, how many times were we going to write that check again? 360 times, 30 years, but it's monthly, right? So the house costs $300,000, but how much are you actually going to pay for that house? Is that a staggering number to you? That's how the world works right there.
So that minus 300,000, that's how much interest.
Exactly. So what's that number? That's what you paid in interest. Now, is that fair? Kind of and not kind of. Now, remember, you did move into the house before you had $300 to pay for it. So it's like you basically spent someone else's money. Like they shouldn't just give you money because they like you. So it makes sense that if I want to move into it before I'm like drinking cranberry juice and stuff, it makes sense that somebody would loan money, but it's like they deserve some money for it. But did they deserve $200,000? So it's like that's 3 Mercedes Benzes, man. That is a lot of money. And by the way, when I bought my first house, the interest rate was 7%. And when you do that, you're paying triple for the house. You're paying $900,000 for the house. 4% is actually awesome. That's a really great interest rate. But even then, you're still paying a lot. Like you got to understand this stuff. You know what I'm saying? That's part of the reason I'm showing you. This class isn't a financial class, but in every class I teach, if I have any excuse to show the order of operations, I was like pulling this up. For me personally, when I bought my first house, I realized very quickly that you gotta get your loan down to 15 years. If you redid this calculation with a 15-year loan, the payment is not double. You'd think it'd be double, right? Because you're paying it off in 15 years instead of 30, but it's actually not double. And that interest rate, that amount you pay for that is way less. It's actually not near as bad. And so that actually got me into the house kind of world. Like I bought a fixer-upper, I sold it, did it again. I did it a whole bunch of times so I could get down to a 15-year loan because that just wasn't okay to me. It's like I worked my butt off. I'm not paying someone $200,000 to sit there and do nothing. That's just not cool. So, does math apply to your life? Well, you can ignore it. And like, there's all kinds of people that don't know anything about what I just said. They're not dead, but man, that's not something to not know. And so for me personally, the fact that I can kind of calculate that by hand and understand that a little bit, that feels good. I mean, I don't know if I get paid any more in my life or, as a result of knowing that, but it just kind of feels good to understand that. There are some formulas that matter, I guess is my point. It's not just nerds that play with this stuff. Like this affects all of your lives. And there's a few things you want to understand. You're ultimately being asked to take this class because there's probably a little bit of statistics in whatever it is you're going to study. Well, learn it. Like it's kind of cool. All right. So take a look at your sheet now, and let's spend the next 20 minutes looking at that. I'm going to quickly I can see that what I put on there is kind of screwed up, but I just want you to stare at that sheet for a second. Give me just a minute here to try to fix what I'm showing you. And what I want you to look at on that sheet is, first of all, that's the same formulas that you just looked at the other day. But the question is, what am I asking you to do with them this time? So would you agree, like, here's what you don't do when you buy a house. You don't just go to Zillow and find a house and say, cool, how much is it going to cost? Right? Why don't you do that? Well, probably because it's frustrating. Probably because it might cost you much. In other words, you can't just calculate the payment and go, oh, $3,500 a month. Cool. Because that'll be like, oh, I can't afford to do that. Actually, what you do is you work backwards. I don't know if you know this, but the bank will only loan you about a third of your monthly income. So if you made, to keep it simple, if you made $2,100 a month, then you could pay $700 a month. You could pay a third of that because they know you got to eat and drive cars and all this other stuff. So they know you won't be able to pay it off. So they'll only let you spend a third. So does it make sense? In a sense, once you get your kind of final job, that's going to be your monthly payment. In other words, you actually already know your monthly payment. So if you made $2,100 a month, they would say you can spend $700 a month on a payment. Well, then the question would be, how much house can I afford? In other words, what house should I be looking at? Does it make sense you're using the same formula I just showed you, but you're actually using it for a different reason? That's kind of what this is about. So let's just practice this a little bit. We're going to have to do this in this class. So let's just take a look at that first formula. Let me switch gears here. So what I'm doing, having you do here is use a formula kind of for a different reason. So for instance, on that first question, A, does it make sense? That used to be some formula that was like, let's say B plus X equals C. Notice this number plus number equals another number. This is the first question on your sheet, right? And so would you agree that go ahead.
I don't think I have that one.
Did you pick that up? Is that? Yeah, you came in after I set that out. It's over there. Thank you. Thanks for speaking up. So this is the first kind of thing you're working on, right? And so let me share this screen. So would you agree, in a sense, this is the original formula? So again, this is just a practice formula, but what's this formula designed to do? It's designed for somebody to put a number here in like 5, and somebody puts in a number here like 7, and then it spits out 12. That's what that formula is designed to do. Isn't that what the monthly payment formula just did? You put in a bunch of numbers and it spit out the M on the other side. That's what it's designed to do. But what if, like the problem that you have, what if that wasn't the purpose for which you were using this thing? What if these two things, in other words, you actually knew the output, you knew that you wanted to have 8.9 come out. Well, and again, I'll erase this, but in the monthly payment formula a minute ago, wasn't it like we knew the monthly payment had to be 700? And so then it's like gobbledygook on the other side. But sometimes you already know the output you're interested in. I know I can pay a payment of $700. And so in the end, along with all the other numbers over here, we'd be solving for P, the principal. We'd be using that formula for something else. And that's actually more practical. More practical than finding a monthly payment is actually figuring out how much of a house can you afford for the monthly payment that you can pay. So my point is, equations don't have to be used just to go in the order that it's set up. And so the question is, if you're sitting here doing this one, do you understand the logic of how to answer that? Now, perhaps you can see it. Maybe you're, sharp enough that you can just kind of stare at that and get the answer. And you have a calculator, so does it make sense if worst case scenario, you could just guess 2.1 plus 8.4 and just hope it's 8.9? And we talked about this a little bit, but the thing you gotta, and we'll practice this a little bit more, but the key is, does it make sense the person really would just like to know what X is equal to? I'd like to know what X is. I'd like to know I'd like to know what principal I can afford to pay. Well, logically then, does it make sense you wish this thing was gone? Because then I would have X by itself. So the question is, how do you get rid of that? And again, some of you already know this. Yeah, what's the opposite of adding 2.1? Subtracting. So the opposite of add is subtract. So in other words, if I subtracted 2.1 from this side, then wouldn't it actually go away? Isn't that's gone now? Is that okay to do?
Yeah.
Yes, as long as what?
As
long as you do it to the other side as well. In other words, you don't have to guess, what do I add to 2.1 to get 8.9? You don't have to guess. You can just do algebra. The opposite. Over here, I can see that 9 minus 1 is 8, and 8 minus 2 is 6, so I was able to do that in my head. Notice I didn't have to guess to get the answer. Some of you might be good enough with numbers that you were able just to kind of see that. Like you said to yourself, let's see, what do I add to 2.1 to get 8.9? And you were able just to get to see it. But does it make sense that's kind of a foolproof way to do it? So we have formulas in this class, formulas that are on that sheet that I just gave you, where we're going to have to work backwards and figure out something the formula wasn't designed to figure out. And that's going to be a part of this class as well. So notice these just get worse. So let's actually look at that second one. I'm going to write it down. I can't seem to bring this sheet up for some reason, so I'm just having to write it down. So I think you'd agree if the last one you were smart enough just to see, you're not going to be able to do that this time. What number divided by 10.44 is 13.13? Like, you're not going to be able to figure that out in your head. And so I could sit here stupidly guessing with my calculator. Oh, maybe it's 400. 400 divided by 10.44. I wonder if that's 13.13. But the key is just do the opposite. What does this say? The trick to this is to kind of, if you're not good at it, is just to say it out loud. That says y divided by 10, right? What's the opposite of divide? Multiply. So if I multiply this side by 10.44, and the reason that's the opposite is what happens on your calculator if you take 10.44 divided by 10.44? What's your calculator going to say that is? Going to say it's 1. That's why it goes away. It's not so much that it cancels or disappears, it just turns into a 1. In other words, you have one y on that side, which is just y. Solving an equation is a lot like a teeter-totter, a balance beam. Can you put weight on this side? Yeah, you can put 12 pounds on this side, but you also got to put 12 pounds on the other side to keep things in order. So the fact that I multiplied this left side by 10.44 means I also have to balance that by multiplying the other side by 10.44. You see, I don't have to guess. If you understand the concept of how to do the opposite of something. So now I can say, oh, my calculator will tell me what that is. 13.13 times 10.44. It's approximately 137. So y. There's anything in this problem telling me how to round, and so it's like I got a big long number, so I don't want to write it all down. I'm lazy, so I'm going to round it to one decimal place. 0.07 would round up to 1, so that's pretty close to the right answer. Does it make sense that you could check your work here? I could check my work by saying, let's see if 137.1 divided by 10.44. Let's see if that, oops, I didn't. Let's see if 137.1 divided by 10.44 really is 13.13. Notice I didn't get it exactly right. Why didn't I get it exactly right? Because I rounded. So that's important to know that you did that. But that does tell me I got it, right? I'm pretty close to the answer I was supposed to get. And had I left all the decimals in there, then I would have got exactly 13.13. But the point is there are real formulas that do affect your life, and being able to work them forwards as well as backwards like this is kind of the key concept. We won't do this because it's out of our league. We're going to do this before. We're going to do that monthly payment calculation stuff. Oh, it's here. So don't write this down, but just out of curiosity, I'm gonna rewrite that same formula at the top, except for with the calculation that we made earlier. Switch screens so you can see that a little bit better. This is what the monthly payment formula is really used for in the real world. The bank says, oh, you make $2,100 a month, then you can pay $700 a month. And the interest rate is 4%, and you're going to pay it off over 30 years. Does it make sense that we need to find P? In other words, how much of a house can you afford? That's actually what happens in the real world. You don't just calculate the payment for any old house you want, because the bank's going to say you can't buy that one. You don't have enough money. So you have to solve that equation for P. You have to figure out what P is. Doesn't that feel a lot worse than like the 2 little practice problems we did? You got to be pretty good at algebra to do that. Fortunately, we don't have any problems with, equations in this class that are quite that ugly. But that's why you need to be able to be good at using equations for other reasons. This equation was designed, it was built to spit out the monthly payment, but we're using it for something totally different here. So if you could solve that for P, then you would know how much house you could go look for on Zillow. That makes sense. You would know what houses you can afford. And typically, again, do people walking the streets, can they do this algebra this good? The answer is no. So you ask the bank, they will pre-approve you, and they'll say you're pre-approved for $220,000, and that's because they made this calculation, or maybe some machine made it for them, and then you know how much you can go spend on a house. So that's the point of this. The problems that I'm doing with you right now are, sort of playful versions of that. So, I'm sorry? Yeah, notice you got a lot more stuff to get rid of. That's the reason I'm not going to solve that, because it's like, that's really hard. We got to start with some easier ones. So let's try this really hard one on the bottom. This is one of the formulas we're going to be using in this class. So I won't explain what it is right now, but notice it's got a Z and an E and an N. It's got 3 unknowns. And then 0.25 is a constant, like that's everybody's number is 0.25. And so notice I said find Z. Well, notice that's not what this equation is designed to do. This equation was designed to spit N out, but could you find Z? So N is 52. Oh, cool. I can plug 52 in over there. E is 4.7. I can plug 4.7 in there. The question is, could you find Z? Could you work backwards? Notice you got a lot more to get rid of here. I'm going to give you just a minute or two to try that, and then I'll kind of do it with you / for you. The cool thing is when you get done and you find an answer for Z, you should at least be able to check it, because that's just normal order of operations, and see if it actually spits out 52 for N on the other side.